a little bit, okay? You are hopefully familiar with this concept. D is equal to RT. Yeah, of course, right? And this is, of course, a linear function, eh? So if I draw that function, it's going to look like this, eh? Now, so this is D versus T graph. Now, let's take a derivative or slope. Find the slope, right? What is that thing? Oh, dd over. Okay, this is why we never use lowercase d in calculus. Let's just put it this way: delta d over delta t, right? And that's r, right? Hopefully, you know how to take a derivative of that thing with respect to t. That's constant rate, isn't it? So if I graph this thing here, r versus t, this is constant function now, isn't it? So what you get is this. 8. So this is what we get. And then this quantity right here is r. Okay, this r is constant r, that is a function r, a little different, but you know what I'm saying. And then let's chop it right here and call this thing t after t seconds later. What is the area of this rectangle right here then? Feel free to use your microphone. Too much geometry? It's not a trick question. It is really that obvious.
R times T?
RT, right? R times T. You mean this RT right here? Whoa. So clearly to go this side, you take a derivative with respect to T, right? And to go the other side, you find the area. But that's a coincidence because this is like algebra 1 thing, right? So let's do something little more high school-ish, right? Remember this, x is equal to vt. Let's say x is equal to x naught plus vt. I'll call it delta t, it's just to start somewhere off other than 0, right? What that means is really x minus x naught, delta x is equal to v delta t. It's kind of equivalent saying, isn't it? Because x minus x naught is right here. Okay, that's a linear function. So that thing, well, this thing, since it does not start, agree? There's a x and y intercept right there, right? Well, in this case, x intercept, because this is x versus t now, right? So what happens if you find the derivative of this thing? Slope, once again. That's still v now, isn't it? So your velocity function is still constant, eh? This is still constant like this. And then let's see, we chop it. But this time, we're not gonna chop it so nicely because we may or may not start from 0, right? Like that. So this side is still v, constant v, your constant velocity. And this is what we call delta t, isn't it? T2 minus T1. So what is the area of this rectangle then? That, right? You mean this? Whoa. Whoa. Still this relationship, this way is the derivative, and this way is the area under this curve, whatever the delta t region that, right? And this does not give you this function back. What it gives you is it gives you delta t back. It gives you the displacement, not the whole function. You know what I'm saying? Right. Are you a believer yet? Ah, maybe we'll do. Okay. Oh yeah, that was straight. So it's like, come on, right? Okay. What about this? Say we have this thingy. This thingy, of course, looks like this, right? So what is dx dt then? That's a derivative, which is a velocity. That's 2ta. So your velocity is equal to 2t. You with me? Okay. Shall we chop this up? I mean, shall we graph it? So this is a linear function this time, so we'll say it's like that, right? So this is a v versus t. And then we are going to cut it. Okay, that's t seconds. So then this is t. So far with me? Somebody tell me what this side is. Oh, come on. Too much algebra? V is equal to 2t. You know what I'm saying? Okay. Chance to redeem yourselves with geometry. Give me the area of this triangle. You did the formula?
T squared.
T squared. See, I was going for the drama. T squared, huh? This is crazy. It works even if this thing is curvy. So nevertheless, this way you take a derivative, and this way you find the area under this function, right? Okay, those of you physics people, full-blown kinematics equation. That. Ooh, this better work, right? Okay, that thingy looks like this, eh? And this is initial position, x naught, right? Say yes. Okay, now, if we take a derivative of this, dx dt, which is a velocity, and that gives you v plus at, right? Say yes.
Yes.
So v plus at will look like this then, eh? Whatever that is, right? So this is v is equal to v, let's say v naught, because otherwise it's confusing. V naught plus ATA. Okay, let's find the area. Oh, this better work, right? Otherwise, so much for that drama. You guys remember how to find the area of a trapezoid? Or am I kidding? Forget it.
Yeah.
Triangle and a rectangle, how do you like it now, right? So this is V naught right there, right? That tells you this length is V naught right there. And then let's call this bottom side T, delta T, whatever, right? T. So what's the area of the rectangle? V naught T, right? With me? Okay, chance to redeem yourself. How long is that side? Remember, this is V naught. I'm going to erase this side. No! I'm going to erase this side very carefully. Okay. I got it.
It's V minus V naught.
No. Nice try, though.
AT.
AT makes sense? V naught plus AT, you know what I'm saying? So give me the area of this triangle then.
AT, 1/2 AT squared.
AT times T over 2?
1/2 AT, wait, so the total area is V naught T plus 1/2 AT. Of course, it doesn't give you exactly this. It still gives you delta T, x minus x naught. You know what I'm saying? Kinematics equation back. In fact, this is how the most physics books derive this kinematics equation with this shape, right? Those of you taking physics, remember seeing this? So this way is still derivative, and this way you find the area under whatever that weird function is, even if it's trapezoid. Then the logical progression on this dot is eventually I need one more set of this. That, put it here, And copy one more. So logical thought process is this. Eventually, this will be something like this, right? And then question is, what's this area? Whatever that is going to be our displacement, eh? You see the historic motivation why we want to calculate the area under the curve like this? Because that represents the displacement in physics, or this could represent work. This could represent so many other things. There are so many real-life applications of this area under this function. Area under the curve is usually what's called, but area under any function, as you can see. So that's what we'll be doing. And this thingy, it has a name. It's known as integral. This is known as the, instead of integral. You get it? Okay, now we go back, and then first thing is, well, let's approximate this because we don't know how to do it exactly yet. So let's approximate. And these are known as a rectangle approximations. And it's literally what it is. You just draw the rectangles to approximate the area under this curve. And that is the exact curve that we have. Y is equal to x squared. We had x is equal to t squared earlier. Okay, and subinterval of this is a 1 through 4. This is 4 right here. My computer is frozen. Really? This is 4 right here. Okay. Now, how are we going to do this? Well, 4 subinterval, 4 rectangles, right? Okay, this makes more sense, so I'll do this one first. This one is known as right rectangle approximation method, RM. Okay, first you chop it up, right? And then this height, this is 1, 2, 3, 4, right? So this data point is 1 square, and this one right here is 2 square. Too much algebra? This one right here is 3 square. And this one right there is 4 square, isn't it? So the way you draw this rectangle is you just plot these points, well, vertically draw the lines, and you draw these things to the left like this. You get it? From that point you draw it to the left like this. So the right corner is touching the curve. So for that reason, this is known as right rectangle approximation method. Good. Now it's a literally area of the rectangles now. And then your book common factors the width 1, and no, don't do it like that, because on the test and on AP, they give you a table with the uneven width. So that is not usually common factorable. So we just literally multiply it. So what we have is 1 times 1 squared plus 1 times 2 squared plus 1 times, can you read this small tiny writing? Let me zoom in. 3 squared plus 1 times 4 squared. You get it? Somebody tell me what this is. Oh, come on. Oh, come on.
30.
Really? 30. Wow, I'm so glad to know that calculus BC students know how to add. It's not even multiplication and addition, it's just addition now, isn't it? Okay, chance to redeem yourself. Left rectangle. Same picture, except this rectangle has a 0 height. And then this thing is 1 square, this thing is 2 square, and this thing is 3 square. I usually write it on top of, and there's no 4 square, right? And you draw this rectangle to the right like this. You know what I'm saying? Oh, this, what did I do? 3 squares not there. 3 squares here, right? You with me? This is known as left rectangle approximation method. Okay, that is 1 times 0 square plus 1 times 1 square plus 1 times 2 square plus 1 times 3 squared. Tell me what that is? 14, of course, right? If you're smart, you would have just taken this one away, subtract by 16, and then, yeah, of course, that's 14. Now, of course, this one is grossly under approximation. Look at this gap, right? And this is over approximation. Look at this area sticking up, right? There's got to be a middle ground. That gives you the best approximation then, right? Unlike these politicians in Washington, D.C., you have to give a little, and in order to take a little, so you come up with a bill that everybody hates equally. That's how sausage is made. And then we have a bill. You know what I'm saying? Instead of saying my way or the highway. Thanks, Miss Pelosi. Okay, so here is a compromise. Okay, this one is known as middle rectangle approximation method, MRAM. Sounds like a air-to-air missile, MRAM, you know, but different spelling of MRAM, okay? Okay, this same way, you still draw these things vertically, chop it up like this, right? But you don't draw the rectangle on one corner. You draw it in the middle right here like that. You know what I'm saying? This is the height. You draw it in a way that it goes through middle. So that one you cannot see about that. This is 0.5, this is 1.5, this is 2.5, and this is 3.5, isn't it? In our data points. So what we have is 0.5 square, 1.5 square, 2.5 square, and 3.5 square, isn't it? So this area is equal to, punch the as we go, plus 2 times 1.5 square, I'll go down, plus 1 times 2.5 square, plus 1 times 3.5 square. Tell me what you get.
21.
21. And then something tells me this has got to be the best approximation of the real area, right? Because this much cancels that much, this much cancels, approximately there, so right? It's got to be off just a little bit. You know what I'm saying? Okay, well, did you know that your calculator can do this? Yeah. Okay, these are the correct answers that you want to test your programs with, but calculator can find the exact area. Okay, if this thing shows up, I can show you. Okay. Oh, I did not want to show you this. I was going for the drama. Okay. Oh, there are 2 of them now, right? 3 of them? How many of these things show up? What is this now? Zoom? No, I don't want Zoom. This computer is just crazy, you know that? Okay, let's go here. And actually, I'm going to restart. X squared, right? And window. See, first there are 2 ways. One way to impress the heck out of your study date, which is what I'm about to show you. And there's a quick way, but let's do this. This is more important now, isn't it? Right. So 0 to 4 for obvious reason, right? That's 0 to 4, right? And then go down here. So you want 0 to 16, eh? Because this will be 16 on that side. So we graph it. Then this shows up. So far, so good? Okay. And then second, and calculate. So you already know what number 6 is, right? Choose the option 7. This is known as the numerical integral. Okay, remember that shape, weird stretch S shape. Ready? Enter. Left bound, you can scroll, but scroll, you can just press 0. Okay. And right bound, press 4. Ready to be impressed? Here we go. Boom. Oh my God. See, this will impress the heck out of your study date. And you see, 21 and 1/3 is the exact, and this is 21. So wow, this is only off by 1/3. You get it? It's still slightly under approximation, but not by much. So much better than these two monstrosity. Okay, now this is great in study date, but when you're taking a test, nobody does this, right? You need to do this much, much faster. I mean, can you really impress yourself? I know sometimes I amaze myself, but not the same thing, right? Okay, so math, quick way, shortcut, math 9 is the hotkey. This, math 9, which is known as numerical integral. Integral is the name of the game, so press enter. Oh, this symbol shows up. And then left bound is 0 here. And then you scroll up, that one is 4, 0 to 4, right? 0 to 4. And then scroll right, and your function goes in here, which is x squared for us at the moment, right? Or you can just put y1 if you have it grafted already. And then here you put x. Ready? Bang. Oh, that's so much faster, 21 and 1/3. Good. Now, if you have TI-83, which has a different syntax, raise your virtual hand and I will write it down for you. It down anyway. So this is, yes.
I just have a question. What does the last dx mean?
We're going to get to that. Just put dx for now.
Okay.
And I will show you later on exactly what that means. So TI-83 syntax is this. N, I, and T, numerical integral, and then you put your function, comma, your x variable, comma, 0, comma 4 is what you do on TI-83. And it'll give you the same answer. It cannot impress your study date. Okay.